Hey guys, welcome back to the channel and welcome back to part 2 of creating a Boids/flocking algorithm in Unreal Engine and C++. In the end of the last episode, we actually ran into a bit of trouble regarding the initialization of the useSphere component in C++, but since then we have actually rectified the problem and have a solution for that. So let's actually get that out of the way first. So if I run the program at the moment or run the simulation and pause it, if I click on any Boid and go to the Boid blueprint, so edit BP blueprint, you'll actually notice that we don't have a sphere component in the blueprint. But do not fret, because this seems to be a bug with Unreal Engine, or maybe I'm just missing some toggle option, some Boolean value somewhere in the code. But if I come back to the program and show collision, we actually have collisions going on for the Boid blueprints. So let's actually go into the code and see how it's implemented. So let's come inside BP Boid class, and this is the implementation. So in the last episode, I actually tried two variations. One is the get component by class, which did not work. I mean, we do get the component, but we cannot change the radius in runtime. And the second solution I tried was creating a default subobject, but I did that within the begin play, but it turns out that you can only call that function in the constructor call. So again, you can only manipulate the values inside the constructor. So this seems to be the Goldilocks solution, where you create a new object component to this actor and then attach it to the root component of the blueprint, right? So we create the same local flock area declaration and then come here and define the local flock area as new object, useSphere component, a useSphere component, and then we check if we have a component and then set up the attachment to the root component, register the component, and set the creation method to instance. Now, the creation method, I'm not sure if it's mandatory, because I found someone saying it's optional, but again, I did take the risk of not using this line. So make sure you can experiment with it, right? So, and then lastly, we just come and say local flock sphere set sphere radius, and this is the main part of the equation pretty much, right? So there's another thing you could also do. You could come down and say local flock area and initialize radius, right? So init sphere radius. You could actually use this function as well, but apparently it doesn't work. So I was using this function before I used the set sphere function, and the value doesn't actually change in the runtime. I think this is because this function is called in the constructor call, not after it. So make sure you're using the set sphere radius. So once that is done, we can come back to our Unreal editor, play the simulation, pause it, and click any Boid, show the collision. And now if we actually change the value down in the shape area, we can actually see the collision radius changing in real time. And that's the important part here. That's why we went through all the trouble of creating the sphere component in code and not in the constructor, right? So we can manipulate the values in real time. So with the collisions out of the way, the next step is to create the first function of the three functions that define the flocking behavior itself. So we'll be implementing the first function, the separation function. So let's get right into it. Let's open our BP Boid or our Boid header file, and then come down and define a function. F vector separate is going to take a t array of a actor, going to be pointer, and then I'm going to call it local flock. Let's define that. So in the separation function, we'll first add an f vector value of steering, and we'll initialize that to f vector, 0 vector, and this steering value will be added to the acceleration figure. Next, we'll define a f vector separation direction, and we'll initialize that to f vector 0 as well. You don't have to initialize 0 vector every time, but personal preference. Next, we'll initialize a flock count of 0. And then lastly, we just go through the flock. So a actor, a pointer, and I'm going to call this other Boid. I'm still getting used to this keyboard. Local flock, I guess. Okay. I'm just going to use my laptop keyboard at this point because it's getting out of hand. So local flock, and then the first thing we need to do is make sure that we are not the other Boid and the other Boid is not null pointer. So if other Boid is not equal to null pointer or null ptr, and other Boid is not equal to this, then we continue the loop. Once that is done, we can actually first calculate the distance to the Boid, and then we can do that by f vector distance. We can say get actor location and get other Boid dot get actor location. So okay, other Boid dot get actor location, and if the distance to the other Boid is greater than a defined value, and this is going to be the separation radius. So let's come back to our Boid manager and define a separation radius. And while we're at it, we'll actually define a different value which is going to control the separation strength. So strength, and we'll define two getter functions. Separation strength. And we can go back into a Boid class and call the Boid manager here and say get separation radius. If it is greater than the defined radius, then we continue the loop, which means we break out of the loop or ignore the loop basically. And next we'll define the separation direction, which is going to be get actor location minus other Boid dot get actor location. And we'll also normalize it. With that said, we can actually add the separation direction to the steering factor. So steering plus equals separation direction, and then at last we can say flock count plus plus. Then we'll come below and make sure we have somebody in our local flock vicinity. So we can say flock count is greater than 0. We'll do a couple of things. The first thing we need to do is get the average separation direction or the average value. So we can say separation direction or steering divided by equals to the flock count. And then we can get the normalized vector. Okay, I'm actually having a little bit of trouble here. So steering dot get safe normal and then we'll minus ourselves from the steering. So velocity dot get safe normal. And at last, we can multiply the steering equals steering Boid manager, right? So we need to get it from the Boid manager, steering or get steering strength. We don't actually have a steering strength function here. Okay, get separation strength, obviously. So get separation strength. I think that should be it. Now you might notice a bad naming convention here, and that is separation strength is actually the separation speed. So here we are normalizing the steering vector, so we get purely the direction or a velocity with magnitude 1, and then we are multiplying a different magnitude of separation velocity. But when you think about it, we're talking about how strong the Boid is going to avoid another Boid. So if it's going to go slow and avoid it slowly, the strength of the avoidance is pretty slow. If you have a higher value, the strength of the avoidance is higher, so it's faster pretty much. You could use velocity or speed here, but I'm going to use separation strength because I understand it better, right? So, and last we can simply say return steering or steering pretty much, right? And if it's not, then we simply return an empty vector. That should be it. So let's come back to our steer method and actually define the changes in acceleration. And in order to do that, we need to actually get the actors in the local flock area. Get overlapping actors, and we'll put it into the local flock. Static class. We'll come down here and we'll say acceleration plus equals separate, and we'll give it the local flock. Now you might have realized something here. We don't actually need to use the collision layer or the use sphere component to actually detect the Boids, because at the end of the day, we are actually calculating the distance to each Boid. So like in Daniel Schiffman's implementation, where you can take the entire frame or an array of every Boid and run a distance check to every Boid comparing your current Boid and check if they are within the flocking radius and then perform the other checks, right? But I'm doing this because the get overlapping actors only gives you X amount of the given flock, right? So if you have 1,000 Boids, you'll only see 10 Boids, for example, within your area. So we'll only perform distance checks to those 10 Boids. So maybe an optimization plus point there, or maybe not. You guys can actually experiment with it and let me know. So next, before we compile it, let's actually clamp the velocity to a given value. And lastly, we also have to set the rotation. So set actor rotation. It's going to be velocity. Remember, the velocity is the direction. So we can actually call the velocity to orientation quad. And we've essentially created a rotation for our actor. I think that should be pretty much it for now. So let's build everything. Okay, we haven't actually defined the radius here. So let's give it 200 and the separation strength to 300 or maybe even 1,000. So we can explicitly see the separation. So yeah, the Boids are actually separating. We may actually turn this to unlit. Yeah, so they're pretty neatly avoiding each other. And if I increase the spawn count, to maybe 50, to get a lot of fun. Yeah, they are trying their best to avoid each other. So that's the separation function complete. Let's actually go and implement the second function, which is the alignment function. So let's come back to the Boid H again, copy the f vector t array, thing to note here is that all the three functions are actually very similar. The only thing we'll be changing is the addition of certain values, right? So for alignment, we'll be using velocity. For cohesion, we'll be using a average position. So you might argue that you could actually implement all these functions into one big function, but just to keep up with the tidy code where one function does exactly one thing, I tried to kind of separate them into three different functions, like Daniel Schiffman, right? So let's actually define that. And let's copy all this and paste it into the alignment function. We won't need separation direction for alignment, just the steering and the floor count. And come down here and we can say steering plus equals other Boid dot velocity. And in order to do that, we actually need to cast the other Boid into a Boid type. So how can we do this actually? Other actor. So I might have to change the naming convention here. Okay, so I'm actually going to rename that into other actor. And then create a Boid for that. So come down here, a Boid, pointer, and velocity. Yeah. And then we can say steering is equal to steering dot get safe normal. Maybe even for the velocity, and that should be pretty much it. So we collect every Boid's velocity and then average them out, right? So steering minus equal floor count, steering get safe normal, minus velocity get safe normal. So we'll have to define an alignment strength. Let's come back to our Boid manager, copy these properties here. Come back to our Boid CPP and get alignment radius and alignment strength. So return steering and f vector. Let's actually call this function in the steer method. Acceleration plus equals alignment or align, and then we can give the local float. So if I build this, we should have both separation and alignment going on. So let's come back to Boids manager and define both the alignment radius, which is going to be 500, and the separation strength again will reduce it a little bit, 800 probably, and the alignment strength is also going to be 800 or 500 probably. And if I play this, yeah, you can see the Boids aligning to kind of form this migratory bird behavior. So if you have seen geese or duck migrating from one area to another, you might see this constant alignment kind of thing going on. And we actually have changes in alignment because of the separation factor. When they get too close, they kind of break away into a new direction, which affects the alignment of the total flock. So that's pretty cool to look at. But birds in real life don't really follow this uniform alignment principle. They constantly change direction and stuff. So if you've seen pigeons and doves and so on, they kind of have this rapid shifting alignment behavior, and that's what we'll be implementing in the cohesion function, where we'll make the Boid try to move towards the average position of the flock, which will create that rapidly moving behavior or rapidly alignment changing behavior. So let's actually go and implement that. Let's save everything first and then come back to our Boids manager. Again, this is going to be the exact same function or the structure. So let's copy the alignment function here, and let's come back and say cohesion. Okay, define that and copy everything here into the cohesion function. The only thing we need to change is we have to add another f vector, which is going to be the average position. So average position, and we don't have to initialize to anything, and then come back to the other Boid loop here, and then come here and say average position plus equals other actor dot get actor location. And we don't have to multiply the steering here, we can just delete that. And since we're not using the Boid class functions, we can actually remove the cast as well. That should be pretty much it. We'll collect everybody's position, and in the steering, okay, so if flock count is greater than 0, average position divide equals the flock count. Makes sense. And then steering is actually going to be average position minus get actual location. And then steering is equal to safe normal minus this velocity, so our direction, and then multiplied by an alignment strength. So we'll have to define that. Let's come back to our manager hedge, copy that, and then we can come back to a Boid CPP and just change this into cohesion. Change this as well to cohesion. So if we build this, we should have a much more natural flocking behavior. Okay, a quick intermission from the future. While I was editing the video, I just realized I made a big mistake. And that mistake is not calling the cohesion function in the steer method. So if I show you my editor here, so the CapCut Pro, and just about this part, around this part, you guys can see I actually, okay, the camera is not focusing, but I actually built the cohesion function without calling it in the steer method. So that's what this video is all about, a intermission. I'll kind of stitch the outro with this video. So let's actually go call the acceleration function or the cohesion function to the accelerator. So go call that acceleration plus equals cohesion, and obviously we'll give in the local. And the funny part is, in that video, I was trying to play around with the parameters to get that erratic behavior or the erratic movement of Boids, and it did not work, and I kind of left it aside thinking that the parameters were the problem, but apparently not. I didn't actually call the cohesion function. So let's build that, and now we should have that proper Boid simulation. So build is complete, and now if I come to a cohesion radius set it to 300 and the cohesion strength to 400, we should see a much more erratic behavior of the flock. So they are starting out chaotic and then getting into one alignment, which is expected because of our alignment strength is greater than the cohesion strength. But we can actually see some Boids kind of getting off track and changing their direction from the average alignment, and that is because of our cohesion function. So here you can see the flock are trying to move towards the average position, which is making them move out of the flock. And to see that better, let's actually come back to our Boids manager and increase the cohesion strength. So watch what happens when I increase that. So all the way up to 1000. And now you can see that much more erratic behavior, like fishes or insects and so on, right? So they change direction quite often, and the alignment is not as uniform as it was in the previous video, or not the previous video, this same video, but I have some temporal anomalies going on with this video editing. But the problem is solved and the cohesion is working. So the cohesion function and the rest of the functions are working, and we have a proper Boid simulation. With that said, if you guys enjoyed the video and found this informative, make sure to leave a like and consider subscribing. If you want access to project files and source codes, which will be coming out soon, make sure to check out my Patreon. It really does help me a lot. With that said, I'll see you guys in the next episode.